Um, so, I wanted to talk about D3, which is this really nice graphics library, and about how to make good graphics. And there are really two organizing topics that I want to address. One is how to make good graphics in terms of software engineering. So we're talking about maintainability, extensibility, scalability, putting these things together, all the things that we typically talk about as software engineers. But also talk about graphics, how to make a good graphic, and what that means, really. It's, in a way, a more abstract question, but certainly a relevant one. And to address both those questions, I thought it would be good to start by taking a step back and asking a question, which is, what does it mean to be simple? In the context of software engineering, I think that means code that's clear in its design and its purpose. You can read it and you understand it. In terms of graphics, well, what does it mean? Does it mean a small number of colors or bars? Well, I'm going to start with a demo. So here is a graphic, and this is certainly a simple one. So there's just a few patterns that you might see. 3 bars at a time, 5 colors, a sort of S shape along the top. Now if I sort this, then maybe some additional pattern comes into view. You can see the blues are on one side, these reddish colors on the other, green in the middle. And I can go back and forth between the sorted and the unsorted. I can sort it in either direction. And what I'm doing when I'm moving these bars back is hopefully making another aspect of this presentation obvious, and that is you can see the pieces of the graph reconfiguring. You can see them moving back and forth. And this is an idea. This is a technique that Mike Bostock, the father of D3, calls object constancy. And his notion is that if you can see what role a particular piece of data plays in one graph, and then you can see what role that same data play in a different graph, and then you can see how it moves from one to the other, then you've learned something new. You've learned a different level of information about the mapping between one graphic and another. So that is, we can call that another pattern, even though it's not held within either of the presentations. It's held within the relationship between the presentations. Now, there's one more set of patterns that I want to present, and what I'm going to do is just hit this button a few times. What I did is put in a randomizer, a pseudo-random function, and if I do this, if I sit and click on this thing a few times, I don't know about all you guys, but I start to see some patterns. Sometimes I see a sawtooth pattern, or I see a grouping, I see oranges on the end, or tall ones in the middle, whatever it is. And the question is, are those real patterns? Are those meaningful patterns? They weren't intentional. Does the meaning, do the patterns that exist depend on the intentionality with which the graphic was designed? Well, I don't know entirely, but I would claim that there is that sort of graphic. I mean, maybe you could answer that with statistics. We could talk about p-values, but outside of that, what we can say is that there are some patterns that are maybe less meaningful than others. There are some patterns that show up that our mind as a powerful pattern identifying machine can find, but that may not have some profound meaning or something. They may not be useful. So we have these two types of patterns then, these ones that you might group as distractions, and these other ones that get to the core of meaning of what we're trying to present with a graphic, and how to distinguish between these. Okay, well, I want to take one more step back, go through a couple more introductory slides before I get to the technical stuff. So let me talk about vision just a little bit. So there's this guy named Jörg Uert out of the University of Kassel who takes toads. I'm not going to take the time to play the movie, but what he does is takes toads and presents various patterns to them, lines like this, or lines like this, or lines like this, and he can demonstrate that the responses are very characteristic of the frauds, and he can model it with a neural net. That's nice and very repeatable. There are other people, not Ewert, at least as far as I know, who take frog eyes and put them on a stick, and they can find similar patterns. So you take a frog eye and you project patterns on a screen, and you can detect that some patterns stimulate the eye and some don't. So there's some sort of pattern recognition that's going on in the retina. So there is pattern processing capability built into the eye. Now, this sort of experiment, putting cadaverous eyes on sticks, is not done as frequently with humans for whatever reason. Therefore, I can't say for sure that these pattern matching capabilities are in the human retina, but if they aren't, they've maybe just been pushed back to the brain. And either way, we have multiple levels of processing. Here's another eye-related piece of recent research, and I put this one on in part just because it's cool, but it's also arguably relevant. This guy, Blackiston, out of Tufts, took Xenopus toads, tadpoles, and he took their eyes and moved them onto the haunch of the tadpole. And what he found is he could train these tadpoles to recognize light coming into an eyeball that's connected to its backside. So this eye is like this incredibly autonomous unit that's acting even without an obvious neural connection. Very strange, but maybe tells us that the eye has even more autonomous capabilities than we would usually give it credit for. And then in the context of humans, here's a quote from a professor at MIT who says that half of the human brain is devoted directly or indirectly to vision. So we've got these pattern matching capabilities, this powerful eye, and then in humans, all the information goes off to the brain where it's forming all these complicated connections and associations which we can't hope to fully map out. And so through all this introduction, it leaves me with a question, and that is, do we seek to do away with these patterns that I called distractions earlier? Do we try to make graphics as spare as possible and thereby only convey the information that we want to convey? Or do we, on the other hand, take advantage of the pattern matching capabilities of the human brain and throw a bunch of images at people, let them pull out what's useful using their equally powerful filtering capabilities, and thereby derive some advantage? And the answer to that question is, I think, both have some utility. And I think maybe, I talked to our artist in resident, Maskell, about this, and he suggested that maybe there are two different systems, and we've got a mathematical system and a language system, and maybe one would benefit from being carved away, and one would benefit from taking advantage of throwing images at the user. So you have these images that seem kind of random, but there's all kinds of information here that we're processing and we're taking advantage of. So now, finally, I want to stop with my introductory remarks and talk about how to make graphics. But as far as this presentation, if you'll allow me to be self-referential for a minute, how do you make a really good technical presentation? In this case, I think I'm gonna lean a little bit more towards throwing lots of images out there and letting you guys filter them and get rid of the ones that are not useful, hoping that those associations can trigger useful ideas and therefore have some utility. So yeah, I was up late last night. There was somebody, I think it was Paul Clements, who said every slide should have an image on it. I didn't get that far, but I did my best. Definitely there are lots of slides with no images. So anyway, now on to how to make graphics with all this in mind. What is the golden road to maintainable and extensible D3-based graphics? And I'm going to say there are 5 guiding ideas. 1, you need to choose good tools, know your tools. We need to focus on control of scope. We need to utilize well-known patterns. We need to use stepwise refinement, and we need to design graphics to minimize cognitive distance. Now, these are probably in order of increasing abstraction, and some of these final ones are more complicated. I'm not even sure I understand what minimize cognitive distance means, but maybe you guys can help me to work through that. So let's start at the beginning. Here are my proposed best practices. Let's start with the tools. So D3 was written in JavaScript, and if you want to use it, you have to write JavaScript. And JavaScript is a language that is, if you come from an object-oriented background, quite different. It's dynamic with all its behaviors at runtime, prototype-based as opposed to inheritance. It uses functions for everything, and it's been around for a really long time and has changed quite a bit. Now, D3, by comparison, D3 stands for Data-Driven Documents, and it's by comparison a much newer system. It's only been around since 2011. There's a lot less to work with, therefore, but what is out there is really good. There are plenty of examples. The author, Mike Bostock and Jason Davies also have done a great job of writing a lot of outstanding documents, and there's a lot to look at, and we'll look at some of it. So let's look at some of those tools. I want to give some example of how to use some of the tools. So I'm going to start with another demo. This is a D3 graphic. This is, if you don't recognize it, the Sierpinski triangle. And so to make clear what's going on here, this is the first level of the Sierpinski triangle, if you haven't seen it before. This is the second and the third. You can see in each case it's repeating the pattern. It's a fractal that is, in this case, implemented recursively. Let's go right up to the sixth level where it gets a little bit more interesting. All right, now how is this written? Let's actually look at the code that implements it. So let's see. So like all programming, you've got to have a good IDE in order to do it effectively, or you have to have some good editor or something. So this is the entirety, minus the header, of the HTML that is used to write the Sierpinski example that I just displayed. And there's clearly not much here. There's a div. Let's see if I've got a pointer. So we've got a div, we've got this little input here that allows us to take in numbers to describe the level we want to go down to. There's another button, and then here is a reference to the actual JavaScript that holds the definition. So HTML was one of the tools that we need to use. Next on my slide, I think, is CSS. So this is another very familiar tool, I'll bet, for most of you here. And the CSS is something that you know well. If you don't use a lot of SVG, then some of these calls may be a little less familiar, like stroke width and stroke, but it follows exactly the same pattern. And that is all by design. The approach of many graphics packages, ones that I've used, is to say, use our package and we will do everything for you. You don't need to know anything else. And that is quite the opposite of what D3 does. D3 says instead, you have your hard-won knowledge in HTML and CSS, JavaScript. We're going to build off of that. So if you don't have all that background information, it's much harder to work in D3. This is not a beginner's language, but if you do, it's a wonderfully powerful language. Now here is the actual JavaScript, and I don't want to go into this in too much detail right now because I want to talk about how to write that JavaScript. So I want to come back to to exactly what this JavaScript looks like, but that's the definition of the Sierpinski triangle that we saw. So let me go back to my slides now. So we talked about HTML, CSS. Let's talk about the DOM as well. So now if I take, I'm using Chrome here, and I can open up the Chrome debugging tool, and I can go to source, and I can see everything that we were just looking at. But I can also go to this screen and look at the DOM. So here's the document object model for the graphic, and let's see. I'm going to refresh this to make sure that it's fully populated. So here is, look at all this SVG right here. Here's the definition of all those triangles, and this is what D3 does for you. So it takes your code, runs through, and generates all this SVG, which it then ships off to the browser, and then this is what's interpreted in order to draw your picture on the screen. So you can end up writing big graphics, big complicated systems that use no HTML definitions at all, and instead are built entirely dynamically using D3, and that is the way that it's done. That's the right approach, I think. Though some mixture of HTML gives a code that's a little bit more understandable. So scalable vector graphics. We just looked at the browser development environment. I also want to include one reference to testing, since Howie opened us up with that. You can test it with Jasmine. That's a reasonable approach. There are other systems as well. I don't think this does a great job of showing what those look like. Maybe let's look at them just very briefly. And so here are here's some tests. This system is similar to many testing systems that I've used in that it's really good at writing unit tests. It's passable in writing integration tests. It's really hard to write a functional test in it. And it's unfortunate because in many ways, with graphics, it is that end presentation that's the most important thing, and it's really hard to get at that with this sort of a testing system. You could, in principle, take the SVG that's being generated, and you can go and you could parse it, and you could decide if the graphic is generating what you want without looking at it, better than taking a screenshot and trying to analyze the image. But I've actually never gone through that. It should work in principle, but okay, let's now go and talk about the principles that one would use to build these sorts of pictures. So I want to start. Do I have a clock in here so I can know how long I'm taking? We're at 10. Okay, great. Great. So encapsulation, one of the fundamental ideas of computer programming. How do you do it in JavaScript? So some of you are JavaScript experts, no doubt, and for you, many of these ideas will be second nature. But if you aren't, here are some concepts you really need to know. JavaScript is not block scoped. If you take that definition that's sitting there in a couple of brackets and assume that when the brackets close, it's no longer defined, you're going to be in for a surprise. Therefore, your namespace can become easily polluted. One nice approach that I've found that I like for controlling namespaces is to start with an object and then hang everything off of that object. So in this case, I can build everything around CBBO, and then when I go and I write my next module, I could hang that off a different variable, and I know I'm not going to be stepping on myself. Problem is, if you put that line up there, var cbbo, at the beginning of every JavaScript file, then you're going to end up redefining it if you have multiple JavaScript modules that you're calling from a single page. And that can be a problem. Here's a way around it. You can say, if cbbo is undefined, then go ahead and define it, otherwise leave it be. But it's kind of wordy. I've come to favor this line at the bottom. You can just put it at the top of everything, and you know that you're going to keep all of your new variables contained within an object. Here is the answer to the first slide showed how not to depend on block scoping. Here's how to depend on scoping. You use immediately invoked function declarations. So this function runs immediately as soon as this module is read. It defines a variable x, and that x is contained only within the function. Immediately invoked function declarations are your friend if you do a lot of JavaScript programming. Here's another point which pertains to variable hoisting. Here I have two different definitions of a function. One is a function declaration, and one is an anonymous function that's assigned to a variable. And the difference between these is that x, if you call x before declaring it, that's an error. And if you call y, then you can run it even before it's declared. So to my mind, that means this is generally favored, because this gives you more control over where your declarations are made and where they're not supposed to be defined. Now, encapsulation is also relevant for graphics. So here is a description of a graphic. It's one I don't actually present here. In this case, the blank lines are contained in, and the arrow lines are subclasses. This is one that I took out of a really nice book called The Grammar of Graphics, which I recommend. But the idea is, okay, we make object models and we put all our parts of a graphic into it. Great. When you're talking about actually in the how you encapsulate things in the production world, not just abstractly, I want to show an example. So here is a project that I'm working on now. This is CTRP, the Cancer Therapeutics Response Portal. The first version of this was written by Ted Liefeld, and it's a nice program. Interestingly, this program, the entire controller is written in JavaScript, which I had not seen someone do it quite this way before. And it's a really nice approach. I think JavaScript is the future for many of us who spent more time working in Java previously. So come to love JavaScript. Here's the graphic. Here's one of the graphics that I put in. This is a box whisker plot. And in this case, we're taking a bunch of genes and we're trying to compare how they act under the influence of a perturbagen or how they act without that. Since the number, so we have these whiskers are defined based on a quartile analysis of all of the data that are coming in. You may have more or fewer elements that end up in as outliers. So I made this adjustable interquartile distance, interquartile multiplier, which allows you to get to just the number of outliers that you want. You can also make these bigger or smaller, and they push each other aside in a friendly way. And then there's another graphic that's callable from this one. This is the version that we're currently testing. So this is all very new code. So some of it is not beautiful. In fact, this one, in the version that works now, I actually log scale it, so it's not nearly so ugly. But in this version, but the point I want to make with this code is as follows. Here's a graphic, and how many files did I use to define just this piece, not the scatter plot, not the line plot? Only 3 right now. So the slider gets its own file. The tooltip is an independent file, and then the box whisker is a plot. But that is not the only encapsulation that goes on. So let me go now to this slide. I took the JavaScript file that defines the box whisker plot, and I just made a box diagram that describes how the modules sit inside one another. And you've got an immediately invoked function sitting around the whole thing, a box whisker plot, this is the actual functional piece of JavaScript, and then a couple of modules, tip handling just calls the tooltip that's defined elsewhere, a bunch of public functions, and then some private functions. And then for each of these, I took the number of function definitions, which are not enumerated here. I took those and just put a number. So in click handling, there's actually 13 different functions that are described, some of them inside one another. So here you have functions within functions within functions. It reminds me of a little bit of when I used to write C++. And I think this is the right way to approach encapsulation. Java has much more of a hierarchy that involves less encapsulation inside encapsulation, but I think this is the right way to write JavaScript and to get it to all hold together. Patterns. So now I want to talk about software patterns. And by the way, if anybody wants to shout out questions or responses or to jeer or cheer, feel free. Okay, I should have said at the beginning. So now I'm going to talk about some software patterns. And this is really, let's see. Oh, I first want to make an aside and talk about this. So the this construct. And I want to use that as a way to talk about some of the essential language elements of JavaScript. So methods, modules, functions, constructors, these all are the same thing in JavaScript, or at least they're built with the same few tools. So here's a function in JavaScript. Okay, easy enough. That makes sense. And the this in this function is the controlling window. So the this does not show up as a pointer to that function, but shows up as the window within that holds this function. Now here's a way to implement a method in JavaScript. So look here at how it's called, and it does look like a method. And here's one way. You can do it other ways, but this is a way that I like for defining methods. And in this case, the this pointer points to the object definition, not the calling window. Now let's look by comparison with a constructor. Now this is a definition of a constructor. You have to put a new in front of this in order to make this constructor work. Now there is a nice trick that you can use so that if someone calls your constructor without a new, that you impose that new for them. I didn't include that here for lack of space. But well, there's a constructor. It looks an awful lot like a function too. And in this case, called with a new, you can see that the this now looks more like what you would expect with an object-oriented language. It shows you the object that you've built. And now finally, let's see, I have one more example. Yes, a custom assignment of this. So in this case, if you build a function definition, it implicitly creates for you. So if I call that with just an F, then we get what we've seen before. But if I use the call function, then I'm allowed to pass in a variable which becomes the this context. So I've assigned the this outside of the function. So this is a very plastic notion in JavaScript, and you can set it. And don't ask me what this enormous man is going off the diving board. I was getting a little punchy when I was looking for images last night, I guess. Okay, so with all these different thises and all these different constructs, it can be it can be a little trying for someone, again, from an object-oriented background. So this guy named Douglas Crockford came along in 2008 and wrote a hugely influential book, which he called JavaScript, The Good Parts. And I don't want to quote this whole thing, but basically he says that JavaScript has some nice parts and has a lot of bad parts. And we're going to only use the good parts. I'm going to give you a subset of the language that I like and that works well. Well, that's great. But it also means that he has cut out huge portions of the language. He does not recommend that you use new at all. He completely excises it from the language. Furthermore, he went on to write this thing called JSLint, which is useful. I use it because it's a nice way to find some parts of the code that are potentially dangerous or redundant or mistaken. But I also configure JSLint to ignore a lot of the things that he would, by default, identify as problems. I think his approach really throws out the baby with the bathwater. So there's value here, but I would not make this, again, if you're a complete novice to JavaScript, I would not make this the first book you read because it's just way too restrictive. Okay, I want to show another demo. Let's see. So here is a graphic that I wrote for the Bard project recently. Let's cause it to restart. This is off of the production system. And so the way this works is we are able to, we have all of these different assays, and the list of assays can be restricted by choosing from these pie charts up above. And if I start adding additional slices, I add more things to the list below. And as well, so I can take my list, I can restrict it. I can also take all of the elements within the list, and I can present them differently. I can present them, doesn't show up very well on the screen, but I can present them in a hierarchical form, where now I've taken those categories that were previously listed linearly around the pie and put them in a hierarchy and say, well, this category belongs to this category, and these children have this parent, and all of these children have this parent. And in this way, I then allow users to take whole sections of the hierarchy and throw them out and say, well, I'm only going to include some of these. And now once you make your selection here, of course the pie reconfigures it to show only the data that is now considered active. It now restricts the pies up above. So now I have two different methods of looking into the data set, one of which is hierarchical, and one of which is instead strictly linear and allows you to pick multiple things. And I still have, you can see over here, I have the restrictions that I made in when I was in the hierarchical form. Over here, I could drill down again and make more restrictions and go back and forth. And so this one I call the linked hierarchies visualization, because you're able to take different hierarchies of information and find out how one branch of a hierarchy connects to another branch of a hierarchy to give you a selection of sets that are constant to the two, or that exist in both of those hierarchies.
Kind of a graphical faceted browser.
Yeah, it is.
Almost.
It is.
But you said you gave us license to ask questions.
Please do.
So, I think Bard is awesome. Really, really well done with design. over what appears to be misuse. Because I find that the interpretability of the graphic is a great thing. You talked a lot about the beginning, but the usability of the graphic is also important. So if at first glance it conveys information, great. But then how does it work when you want to do stuff? And these open the door to abuse of that, because your slivers can become so small you can't even hover over them with a mouse pointer.
Oh yeah.
So like, what's the point of that? Like I see some sites would do that, and I can't even read the pop-ups that are trying to tell me what's in that sliver because the sliver is so small, so the pop-up obscures it, and I can't even touch the sliver anymore.
Absolutely. Yeah, I think that's a completely reasonable objection. Oh, let me see if I can show you what I think one of the utilities of this approach is.
You don't seem to be making that error here because you're not popping up stuff as you're hovering over the sliver. On that, say the protein class in the middle.
Here we go. Yes. Well, I think there is, in this case, what we really have here, I think, are a graphic that could be used quantitatively and one that can be used qualitatively that are working together. I mean, you could certainly get quantitative information out of the graphic. This is not a great example, this particular compound, but in this case, what I'm doing is I'm coloring by those assays that were active. And so in this case, we only see one of these sections, which is organism-based format. Well, I don't even know what that is, but biochemical format, that makes a little bit more sense. If you see that one of these wedges is darker in color, then this tells you that all of the assays that are active may have been in the biochemical format or may be pertaining to a particular protein target or something like that. It gives you a really quick way, at a glance, to know something about the compound that you're looking at and all the tests that it was applied to. But I think your point is well taken. There are definitely instances where these sorts of graphics can be pretty, but without great utility. And I would argue in this case that there is utility, but yes, it's definitely something to keep an eye on. So I want to talk more about patterns. And this is really, well, first, I want to talk about looping. Now, this is just one of those points you really need to know, but just very quickly, iterators are better than looping. Great, use a for each instead of a for. And under ES5, we've got this neat trick for modifying arrays. It's very attractive. But here, this is, for me, the meat of this talk. If you walk away with nothing else, I think this is the useful part. Here are the patterns that I think are most useful for defining good JavaScript and putting it into packages that are reusable and interesting, or easy for other people to understand. So first, the closure pattern. This is a good one if you want to really have an element that's private. There is no way to get to this parameter, which you can get it through this method, but there's no other way to sneak into this function and to be able to access this information otherwise. Another pattern you can call the object pattern. This is a nice one if you're going to be using news. And this is a nice one if you want to fill up a bunch of objects that you're going to then be able to reference later. Okay, good. Another useful one. This one is one of my favorites. Stefan Stefanoff calls this the module pattern in his excellent book, JavaScript Patterns. And this one's really good if you want to define a library. So here we've got an immediately executed function, and then we have, in this case, just a getter and a setter, but it could be whatever you like. And the immediately executed function returns this object, this block, and that block has definition references these two functions. So you define your functions, however many as you like, up in this section, and then those that you want to make public, you copy down here. Otherwise, they remain as private. So if you want to build a library, this is a great way to do it. If you want to define objects dynamically, it's a little less useful because this is immediately executed when the module is first defined. But there are ways around that. You don't have to put it inside an immediately executed function, but okay, this is just, we're not talking about all different ways of putting this together. We're talking about some basic patterns. Here's a different pattern. This one I'm going to call extensible object or extensible objects. The way this one works is I've got a function definition, and then I'm going to define this thing called holder, which is an object, and I'm going to return that pointer to holder. And now I go through this function and I add I add as many elements as I want, get parm, set parm. I can add whatever I want, and all of these are callable. And then this is, not only is this a nice useful pattern and allows you to build objects and extend them, but it also is very similar to the way that D3, one of the common patterns that's used in D3. So this is one to bear in mind. Well, we're going to now get to some D3 code. So here's the first time that I've actually put up on the screen some D3 code. And what that means now is code that's used to call D3. Those are written by the user, and the definitions that are specific to D3 are here, here, and here. But the idea is that you write this code, and it's going to put some circles up on the screen. Now, note that each one of these methods that is called returns the object, the holder in our previous example, that allows you to then stack these up and have them follow one another. This is similar to the builder pattern in Gang of Four. And this is, you can string as many of these together as you want, as long as each time you return that holder object, again, from the previous example right down here. Now, here is the construction for getters and setters that is used is frequently used and recommended by many authors in D3. So here's a getter/setter. Instance width, instance here, this is like holder in my previous example, is assigned an anonymous function. If there's no arguments, then return the width in this case. Otherwise, define the width. So if I call width with an argument, I set it. If I call it with no argument, I return the value of width. And if I'm not using it that way as a getter, then I return instance so that I can string these together. So if I'm using them as setters, I can put as many as I want together. If I'm using them as a getter, then that has to be the final one in the line. So this is the way that you write getters and setters in D3, and it works nicely. So now here I want to put together those ideas that I just talked about into one big example, because this is really core stuff for writing D3. So here I've got a function called myChart. I've got this function instance, where you put your chart generation code, and then here's a getter setter, and then at the bottom I return instance. So if you write code like that, you can make nice big modules that look like D3. Now, I want to move to a slightly different topic. I want to talk about stepwise refinement. I've got a demo here. I wonder what this one is. I thought it'd be fair after going through all those patterns to do some sort of a graphical presentation, just so that people don't have their eyes get too glazed. So this is the familiar Mandelbrot set, right? So we've got the complex plane. You take different points in the complex plane and you iterate on your solution and see how long it takes to go to infinity. This is probably a really bad choice of graphics to do in D3 because it's pixel-based. And D3 specializes in vector graphics. So you can do this in D3. I think I did it on a otherwise uninteresting Saturday afternoon one day, but other than using the other techniques that we were just talking about, maybe not especially relevant. Just a break. Okay, now we're back to informative presentation. So this notion of stepwise refinement, Nicholas Wirth talked about it way back in the 1970s, and perhaps it's even more relevant in these days when everybody, or many people talk about agile methodologies and quick iterations and providing code that changes in response to users' desires. In the context of data-driven documents, though, it's even more relevant because Bostock's idea is this. You take your DOM, so you've got a bunch of structures, and now you start attaching data you hang the data off the different elements in the DOM, and then you can go back later and you can display it however you like. The data are in the DOM, and now you can decide how you want to display it, and maybe display it multiple times in multiple ways. And so I talked about the Crockford effect before. This is the Bostock effect. So Mike Bostock, he wrote a graphics library called Protovis when he was a PhD student at Stanford, and then he left to make D3. He wants to minimize the distinction between data storage and visual representation. So his word for this is representation transparent approach to visualization. It's a nice approach. It's powerful. His terminology for describing its benefits are accessibility, which means you know how to do this because you already know CSS and HTML and SVG and all the rest. Expressiveness, how powerful the graphics are, and you can really do whatever you like with the graphics, and the performance. And it is very performant, even with large numbers of data elements. And we've got another demo, apparently. Okay, great. So this is an example of taking data, hanging it off the DOM, and then being able to display it in different ways. And this is one that was written with a library called, I don't even remember quite what this is. This may be, this is crossfilter. This is an example of how to use crossfilter. So again, we've got this big long list of different data elements, and as I choose those, you can see the different, you can see the list restricting and growing, et cetera, and all of these work together, and all of them can be simultaneously adjusted. So it's a nice example, I think, of how you can, you take your data, you put it in your DOM, and then you can adjust it with multiple graphics, potentially at the same time, all working on the same underlying data set. Okay, so now I want to talk about the core of D3. I want to start really narrowing in on what D3 is and how you use it. So one of the core ideas of D3 is the selector, and now W3C also has selectors, but they return an actual DOM element. When you make a selection with D3, it returns an object that contains the DOM element, but also has some other attached elements. And in particular, it has the data that you may be hanging off the DOM. There's select, which returns a single element, and select all, which returns all elements. So in the Sierpinski example I started with, if I say select all, I can count the triangles, and then I can also affect all of them at once. Now, select all is nice because it allows you to operate on everything that came back at once without a loop. So if I do a select all and it comes back with a bunch of polygons, and then I say, well, oops, I don't click on it. I use my pointer and I say, well, okay, I'm going to change the fill on every one of those polygons. Then it will loop internally through and apply this function to every one of these polygons. Now, this is done just for illustrative purposes. Typically what you do is you put a function, a variable in here, a D or maybe a D and an I, and then every one of the elements that's hanging off the DOM will be passed in through the D, and then the I is an index. So you then would reference D in this function here, and you can make every one of those objects a little bit different. So this is a great way to loop through vast quantities of information with this single function. Now, here's a different type of looping. Now, in this case, I can do, I'm going to take a selection. So here I'm taking, so I've used select, and I've pulled back a bunch of data, and I'm going to call this chart and create something. Now I'm going to take the data, and I'm going to loop through it. So most of your D3 code is going to have a line that looks just like this, where it says, however many elements you pass me, I'm going to go and I'm going to create a chart for each one. So if you only have one, then you might get that box whisker plot that we saw early on in the CTRP example. But if I pass it a bunch of data, then I'm going to get multiple boxes and multiple whiskers, each presented on the same graph. Now, here we see looping on the basis of the each construct, whereas previously we used select all. And so the difference between these is what? The difference between these is that here I can put a bunch of functionality. I can put a bunch of work inside that each loop. I can change and do different things as I like. Whereas if you're using select all, I only have a single statement that I'm looping through all at once. So two different kinds of looping. Often you put them inside one another, but again, this is the core of what that D3 code looks like when you're making any of these graphics. Now, here is a particularly novel approach that Bostock uses. He uses enter and exit subselections. And the idea of this is you perform your selection, your select all, and from that, you take your select all and you put an enter call on it. And what you say to the package, to the library, is, I'm going to define some points right now. The next step frequently is to tell the system, okay, change those points however you like. And then finally, you have a select all with an exit. And anything that wasn't included in that select all is now dropped from the total collection. So this allows you to add things to your graphic, modify them, and then remove any nodes that are no longer relevant. And this is pretty obscure the first time you see it, but it starts to make sense. And it really is of the essence for D3 programming, and it's crucial for dynamic visualizations. Here's an example of how to use it. So first I have a select statement, and I'm going to select the body. This is a typical HTML body. I'm going to append an SVG element onto it. Then I'm going to go through and I'm going to take the SVG that I define here, and I'm going to say, okay, select all the polygons. And now put some data. So now here's the process of hanging those data elements off of my DOM. And from that, I'm going to generate a new variable, which I call triangle. I must have stolen this from the Sierpinski example. Then I do my enter call, and I actually append the polygons, and then I do my exit and remove them. And if there are any polygons that aren't referenced, then they aren't included. Now, this right here, when you're saying select all, those polygons don't exist. You're telling D3, make a placeholder. I'm going to give you some polygons later, but make a placeholder and just assign the data. Save the data and get ready to add polygons. Then when you get to the enter call, that's when you actually append the polygons, and the exit call removes them. So again, this is perhaps the single strangest part of D3, and this is one that's it's good to step through with your browser before you can really get to understand it at a deep level.
Cognitively or semantically, the notion, language is shaped the way we think.
Yep.
And how can I select a thing that doesn't exist yet?
Yeah.
Why don't they say define all? Or why is it a word that says pick something that's there, used for something that isn't, to take something that isn't there.
Great
I
question.
don't quite get that.
Yeah, great question. I don't have an answer to that. I think that would have been a better choice than enter and exit, but that's what he does.
Enter and exit, I get. The select all, which is like, make a bunch of stuff, placeholders. I love the idea. I like sticky data in random spots in the DOM and all that. That's cool. But I'm just saying that intuitively,
Yeah, well, I think he's trying to keep his API minimal.
really clean.
Yeah, so he has a very small set of operations that you need to learn, but that's one of them. Please.
So you asked Boss like that exact question, like what, what is that? How did you model this concept? He actually likes the concept of the stage, right? So this first select stage where we say, okay, we're going to select all polygons. It's defining a stage which your actors are going to play. So for him, everything is just saying, okay, well, just like any theater stage performance, right? The first thing you do is you define the space in which that thing is going to play out. Initially, there's no actors, right? You're just saying, here's the boundaries of what's going to happen, right? In this case, boundaries are polygon objects, right? From there, you're going to start giving it actors or data, in this case, and actors can do one of three things. They can enter the stage, they can move about on the stage, which is up and in, or they can exit the stage, right? And so I think, even though you're right, the language is a little wonky. I think the analogy there, it's like, so none of this really made sense to me until I heard him describe it that way, and it was like kind of clicked right away. But anyway, I think that's the intention that he has.
Oh, that's great, Corey. Did you talk to him when he was here at Visby or some other time?
Yeah, I mentioned it briefly, and I was sure that you gave the same answer that I saw him some talk he was giving like a year before.
Wow.
So he's consistent in that now.
That's a great analogy. I like that.
You described exit as remove, but then you actually said exit remove.
Yes.
Is that always the way you use exit, or do you do lots of different things with exit?
No, you typically remove it. So what you're saying is exit tells you these are the things that I am now going to act on, and in this case, I'm going to act on them by removing them. So it's typically exit, remove. I mean, there may be some other examples, but that's the way I've used it. I don't know, Corey, if you've used it other ways.
The reason it's split out that way is for one to do things as your data is exiting.
So exit just is essentially giving you the list of things that weren't operated on.
Mm-hmm.
So you could change data if you wanted to there. It's just typically you just remove.
Right. So a really common pattern is all this is chain. Concept of transitions, right? So you can tell a point in your graph, I want you to contract to zero radius over 500 milliseconds, right? So a really common pattern is to say dot exit to grab your exit subselection, dot transition in some logic, and dot, right? So it's the same thing.
Yeah, I can see how the remove works and why, it wasn't automatic. I expected exit to be that. And when I saw remove, it just opened the question, what else would you possibly do?
Yeah, well, it's a good point. He does use a lot of transitions. So, specifically define a transition, and then this allows you to get to that those moving animations and the object constancy that is important to his approach.
I wonder if anyone here has used the GTK library today?
I haven't.
Because they have the event callback mechanism allows you to add sort of arbitrary parameters, and those parameters can be objects which you can define in arbitrary ways. It resonates very much with what he's doing here. Of course, it's in a different context. It's not in a browser, in a DOM, but it's in a programming language like C and then wrapper languages around it and stuff. So if you take GTK and that notion of event callbacks, and then you use a language like Python, you can do stuff that's very, very similar to this, because you can define arbitrary objects, arbitrary structures, stuff arbitrary data, and arbitrary things, and then pass them around in all really very flexible ways, which sounds a lot like what this data stuff is. You're putting stuff in DOM. So it's like you're squirreling data away.
Yeah.
Later on. It's kind of cool.
Huh. It's a good parallel. Okay. Well, I think we're getting close to the end now. Okay. So here's the most abstract part of all. Cognitive distance. What does it mean? And let's see. I think I'm gonna push ahead without the demo right now. So there's this guy named Donald Norman who put together this book in 1980 called The Design of Everyday Things. And it's a nice idea that those sorts of tools, those sorts of handles that take advantage of physical analogies and cultural standards are easier for us to remember and take advantage of than those that are pure abstractions. So he uses a steering wheel where I pull it to the right and the car goes to the right. Or he talks about a car stereo where if I have the left-right speakers and I turn this button, then okay, the speakers are going to rise and fall. But if I try and do the fade left to back to front, then for me, it's I know I often find I'm forgetting, well, okay, you know, which way do I turn the button to make the back speakers get louder? And so he talks about the idea that some representations are more natural and easier for us to remember and to take advantage of. Now, how does that pertain to scientific graphics? What's the parallel there? Well, one connection is this notion that every graphic is a mapping. So I have some physical space, you know, the physical space of data, if you will. You know, I'm talking about genes or heart disease or whatever it is I'm talking about. And then I have the pure graphical space, in this case represented with a P, and then I go from one to the other. Now, if you can make these continuous in the sense that small changes in the physical space lead to small changes in graphical space, or vice versa, then this is advantageous and makes for good mapping that's easier to work with. If they're discontinuities, then that's a mapping that's less useful. But many of the types of data that we work with, it's difficult to see what the obvious mapping would be. So, you know, this is, it's a topic I don't have a great way to approach it, but I can see cases where this question arises. So one instance is for me when I'm looking at data. Let's say I'm looking not necessarily at raw numbers, but maybe I'm using some sort of a graphic or some other abstraction. And at first I just see numbers. And then I think, well, wait, I think I see something. I see a pattern in those numbers. And now I'm going to find some verification technique. Maybe this is statistical, maybe I'm going to make some other graphics, maybe I'm going to do something else. I'm going to test that pattern, and then I'm either going to validate it and say, okay, this pattern exists, I can use it, or I'm going to invalidate it and say, well, no, that really wasn't a pattern. That was like those random sawtooths that we saw in the beginning, and then I go back to the beginning again. And for me, this step right here is particularly interesting. How do we recognize the patterns that exist in the data, and how can we express the data in such a way as to make those patterns easier to recognize? And to me, this gets back to this notion of representation. And if there's a way that we can represent the data so that it has a natural mapping to the underlying structure of the data, then we allow people to make this jump and to be able to find patterns that otherwise they might not see. But again, this is the area where, you know, I have to struggle a little bit, or maybe a lot, because I really don't have a clear idea of what this all means, or at least one that I feel confident in. Is there a mental landscape? You know, if I have an array of numbers here, you know, 1, 6, 9, 13, is there a mental landscape that I can map this to? Is there a way that I can represent those more naturally than in any other way? I don't know. If I have a bar chart where each width is the number, corresponds to the number in the array, that seems like a very natural mapping. If instead I take that same array of 4 numbers and now I build it into a pie chart, well, is that a less natural mapping? Maybe in Cartesian coordinates it is. What about if we're working in polar coordinates? Maybe it's a more natural mapping. So what does it mean to have a natural versus a more forced mapping? Any ideas? Because I really don't know. Yes?
Well, we wrestle with this in design databases, for example, for representing scientific information. And I try, and it's actually, it takes a lot of effort to stop software engineers from making implementations that resonate with their desire to organize data according to the concepts present in a language or in a database, rather than the semantics of the domain in which this software is intended to exist. So or organize things by genes, because the biologist that will resonate to a biologist who's been steeped. Now, what resonates to us is not necessarily an a priori biological thing you're born with. It's a product of your training, culture,
sure.
And experience. So two different people can look at the same thing and say, that's not my mental landscape. But a biologist, for example, in this domain is going to have very semantic-oriented mental landscape. And so they're going to want to see things that resonate with that. They're going to want to see information organization which resonates with that. That's how I ask our team to actually approach these.
Sounds good. Any other ideas? I mean, domain expertise. That seems critical.
Oh, no, I was just thinking that when there's an object-oriented programming, normally I would try to mimic the object depending on what the base state, just like as Mike was describing, where I would try to get it as close to the real world as possible, because normally when I look at something, I don't think that bunch of objects looks like an arrays. I normally think this is a jar of marbles.
Right.
So it helps me step away from what the computer understands more to something I can understand, so that I spend fewer, break minutes processing what the computer should be doing for me and thinking more of the problem.
So you map it into a familiar visual image?
Yeah, so a way to essentially build up the language so that I don't have to think in terms of the language, and I can think almost entirely of the real world and its problems.
So I think that mapping, F:(S to P.
Yeah.
It's almost like you said physical space to graphic space, right? It's almost like semantic space to graphic space is maybe even more encompassing generalization of that, or statement of that, because it is your mind's way of interpreting information that you're really trying to map to some picture. So that's what came to mind.
Okay. Well, that's great. Thanks. This is one I'm going to continue to struggle with. Let me just close up and say I want to acknowledge the chemical biology platform, much of which no longer exists, but did a little while ago, and also some other folks here at the Broad who have helped me in various ways over the months and years. And then finally, here's some books. These are ones that I recommend. You'll note that these are almost all JavaScript books. There are no D3 books, and I've read a few of them. It's such a new language. I just haven't seen the really authoritative book that's come out on D3, the one that I think holds all the ideas at once. So I've got 4 JavaScript books up here, including Douglas Crockford's, this awesome Grammar of Graphics book. But I would say, as I mentioned before, the writings of Mike Bostock are awesome, really deep, full of interesting stuff. He's all, it's all available online. That's the place to start if you really want to teach yourself D3. That's it.
So one question that comes up for me when it's this great responsive graphics, what about when you don't want it just in the browser? What kind of options do you have for taking that from the browser to your back end? Did you have to wrestle with that at all?
You mean, well...
You want to have reports, or you want to make...
Right.
You've explored something, you want to save that.
Right. So SVG is what's generated by D3, and that SVG is immediately importable into graphics programs. So like Illustrator will read as an SVG file.
Copy and paste.
It's copy, yeah, well, you can't, yeah, you don't want to do a screen capture, but you take that SVG and you pop it right into a program like Illustrator, and then you get, full vector graphics with an arbitrary degree of precision.
You lose the data connection.
Yeah, then you can't change it anymore.
Right.
Then it's static. So
yeah, that sort of iteration and sharing that you do get when you have it on your server.
yeah.
That's what I'm getting at.
Oh, I see. Yeah. Sure.
From the browser, because we encountered this problem on the user's messages. Oh, what is that? SVG, I don't know what that is. Can I download the app?
Yeah, I don't know how to do it directly from the browser, but again, if you import it into Illustrator, then you can export it in whatever you like. So,
There's also, it should
Yeah.
be possible to automate that. The command line, there's a command line tool package called Image Magic, which does all of this stuff.
is that right?
Yeah, really. So if you don't mind.
When people are browsing, and mostly biologists, when you tell them, load this into Illustrator, they don't want to do anything. They want to just a button.
Yeah.
Sure.
You can always print as a PDF.
SVGs are becoming so ubiquitous now that within the next year or so, they're just because they don't recognize it doesn't mean they can't download it and stick it wherever they want. In fact, even now, most things, just because they haven't heard of it, doesn't mean they can't use it. They just don't realize they can just grab it and stick it in just about anything they want.
Yeah, so I also said that for some of the work we've done with the connectivity map, very, very similar techniques. We have already a prototype of a version that is just a button you click to get a PNG back. So that can be extended to whatever camera you like, if you want PDFs or tips or whatever. Under the hood, what we're doing is we're actually reading the DOM of the SVG, rendering it out to a canvas element, HTML from canvas. It's very easy to port to whatever pixel display right now.
I'm sorry, you wrote a tool in JavaScript that does that?
We're running a couple different libraries. There's I can send you a mail about it.
Oh, I'd love to, yeah.
But I mean, there are routes in the browser as well. I think conceptually they're all very similar to what you do in command line with a program like Image Magic. We'll hack your browser is a little bit more constrained, but this library is good. We've had some success in this kind of prototype.
You alluded to something, great talk by the way. I really like your emphasis on big picture concepts.
Oh, thanks.
You alluded to something here that the D3, because it's SVG, is more vector oriented. You don't want to draw pixel level scale graphics. So, which means there's a gap between this kind of visualization and say volumetric. Anytime you want to do true 3D volumes, not just surface renderings like games, a lot of games do with tessellated surfaces. What would Bostock or maybe you say about that gap? How does you still have to use WebGL or you still have to use OpenGL or whatever. There's something there's something that is as cool as this doesn't exist in that domain yet.
Yeah, that's true. I mean, of course, in principle, it's just a set of transforms along with hidden line algorithms to be able to make that 3D appear. But in practice, 3D is much trickier, and there are all those shadows and perspectives to worry about. There, of course, as well, it takes a huge amount of processing, and browsers are now powerful on everybody's desktop so that you can do these 2D graphics. Bostock has not addressed the 3D question wisely, I think, because it's a big can of worms. If somebody else would, I think that'd be really advantageous. I don't know if anybody else has any experience with that, but.